The Lovász theta function theta, g, is a polynomial time computable upper bound on the stability number of a graph G, achieved through solving a semi-definite program, SDP. Researchers have attempted to enhance the theta bound by applying the n plus lifting operator of Lovász and Schrijver to the classical maximum stable set problem. This paper explores the application of the n plus operator to two distinct linear formulations based on clique and nodal inequalities. Computational experiments involving larger graphs than those previously documented show that stronger upper bounds than theta, g, can be achieved with a reasonable additional computational effort, particularly using the clique-based formulation for sparse graphs and the nodal-based one for dense graphs. The paper addresses the stable set problem, SSP, which aims to find a stable set of maximum cardinality in a simple undirected graph. In graph theory, the stable set problem, SSP, seeks to find the maximum weight stable set in a graph G, denoted by alpha, G. As an n-fard problem in the strong sense, SSP is equivalent to the maximum clique and set packing problems. The SSP can be formulated as a binary program using edge inequalities, defining the fractional stable set polytope frac, G, and the stable set polytope stab, G. Studies on stab, G, have identified various classes of valid inequalities, often associated with specific subgraphs. However, linear relaxations based on these inequalities typically yield weak upper bounds on the stability number of unstructured graphs. To reduce the performance gap with fast combinatorial exact algorithms, sophisticated cut generation procedures are necessary. The theta number of a graph, theta, G, provides an upper bound for alpha, G, computable in polynomial time by solving a semi-definite program, SDP. As a powerful tool in graph theory, theta, G, enables polynomial time solutions for SSP in perfect graphs, often offering significantly stronger upper bounds than linear relaxations and mitigating numerical difficulties affecting SDP algorithms. The n plus lift and project operator has been applied to the LP relaxation of SSP, yielding a stronger SDP relaxation. The strength of this operator is demonstrated by its implications on facet-defining inequalities of the stable set polytope. It has also been used to identify additional graph classes for which SSP can be solved in polynomial time. Recent studies have focused on graph classes that produce stable set polytopes with high rank with respect to n+. Computational complexities arise when employing SDP relaxations to strengthen the Lovász theta bound. Experiments with n+, frac, G, and related variants demonstrate that these relaxations can yield stronger upper bounds but at the cost of increased computational effort. Solving large-scale SDPs necessitates specialized methods, and large instances are difficult to manage. Alternative methods, such as those presented by Gar and Rendel, and Locatelli, achieve strong bounds but still require significant computational effort. This paper aims to bridge the gap between the Lovász theta bound and computational effort by presenting new SDP relaxations derived from applying the n plus operator to alternative LP relaxations. The first relaxation is obtained by replacing edge inequalities with clique inequalities, which can lead to more compact and tractable relaxations. The opposite rationale derives the other SDP relaxations, which start from more compact but weaker LP relaxations and rely on the ability of the n plus operator to recover their potential weakness. The paper investigates a hierarchy of SDP relaxations, with the primary level consisting of applying the operator to a surrogate relaxation of frac, G, with O, V, inequalities. Coefficient strengthening procedures then derive two progressively stronger relaxations, with the first taking polynomial time and the second requiring the solution of n-fard subproblems. The paper proves that all proposed SDP relaxations are at least as strong as the Lovász theta relaxation and compares them to each other and to n plus frac, G. Implementation issues and experimental results are discussed, showing that significant progress is achieved in several cases, with relaxations obtained from clique inequalities being more effective for sparse graphs and those from nodal inequalities being the best as graph density grows. The increase in computational workload required to improve the theta bound is significantly smoother than that of previous approaches. The lift and project operator is a method used to generate valid inequalities for a given polytope. It involves 3 steps: lifting, linearizing, and relaxing the quadratic constraints. The lifting step generates quadratic inequalities that are valid for the polytope's linear relaxation. These inequalities are then linearized by introducing a matrix variable x, which is used to rewrite the quadratic constraints. Finally, the quadratic constraint x equals xx is relaxed by requiring x minus xx to be positive semidefinite, which is equivalent to the Schur's complement condition x minus xx0. This relaxation is significant as it enables the generation of valid inequalities that can improve the bounds obtained from linear relaxations. The strengthening step in the convex relaxation method involves adding constraints to the original system, resulting in the definition of the convex set M plus P. This is achieved by introducing a lift operator M plus, which satisfies conditions 4, 5, and 7. The set M plus P is obtained by taking the intersection of the sets defined by these constraints. In the projection step, M plus P is projected onto the original X space, resulting in the set N plus P. Lovász and Schrijver showed that N plus P is a valid relaxation of the polytope of independence pi, meaning that pi is a subset of N plus P, which is in turn a subset of P. Notably, N plus P is a relaxation of pi despite M plus P living in the lifted variable space. The linear inequalities x is less than or equal to b are trivially satisfied by M plus P. The original constraint can be recovered by summing the linear inequalities defining M plus P. Moreover, the definition of M plus P and N plus P does not depend on the representation of P, but only on the set of points in P, leading to property 1. Given 2 polytopes P and P, with P subset equal P, then M plus P subset equal M plus P. Lovász and Schrijver provided necessary conditions for an inequality a Tx is less than or equal to b to be valid for N plus P, as stated in lemma 1. Specifically, if a Tx is less than or equal to b is valid for P intersection x underscore I equals 1 for all I in V, then a Tx is less than or equal to b is valid for N plus P. The paper then shifts its focus to continuous relaxations of the semidefinite programming (SSP) problem, recalling known results about linear and semidefinite relaxation of the SSP. This section of the research paper discusses various linear relaxations for the stable set polytope stab G. In a graph G, it highlights that several classes of valid inequalities have been identified, including clique inequalities and rank inequalities. Clique inequalities are defined as summation text I element of C xi is less than or equal to 1, where C is a maximal clique in G. These inequalities induce facets of stab G and can be exponential in number, with an associated separation problem that is n-fard in the strong sense. However, effective separation heuristics make this class of inequalities computationally manageable. The paper also discusses the O1 linear program, which is a valid formulation for the stable set problem if C subset equal K is any collection of maximal cliques covering all edges of G. This formulation has a number of clique inequalities bounded by E, and typically contains fewer inequalities than frac G. The paper notes that formulations based on a greedily computed minimum size collection C are competitive in practice. Additionally, it explores other rank inequalities of the form summation text I element of S xi is less than or equal to alpha G S for vertex subsets S subset equal V inducing special graphs. Examples include odd-hole inequalities, web inequalities, and anti-web inequalities. Web inequalities take the form summation text I element of W xi is less than or equal to Q for every vertex set W inducing A P Q web, while anti-web inequalities take the form summation text I element of A xi P Q for every vertex set A inducing A P Q anti-web. The paper further discusses a different modeling rationale pursued by Della Croce and Today, who considered the surrogate relaxation of formulation, 1, obtained by summing up, for every I element of V, the edge inequalities over all j element of gamma, I. This yields the nodal inequality, summation text j element of gamma, I, xj plus, gamma, I. Xi is less than or equal to, gamma, I. Murray and Church observed that this relaxation can be strengthened by replacing, gamma, I, with any value ρ is greater than or equal to alpha, g, gamma, I, resulting in a class of O1 linear programs of the form given in the paper. In the 7th page of the research paper, the authors delve into the formulation of the maximum summation display problem, focusing on the coefficients ρ. They introduce the concept of nod, g, r, to denote the polytope defined by the inequalities, 9, and non-negativity, where r can be gamma, theta, or alpha. The authors emphasize that nod, g, alpha, is a subset of nod, g, theta, and nod, g, gamma, highlighting the importance of these relationships. The page also explores SDP relaxations, specifically the Lovász theta relaxation. This involves introducing quadratic variables Xi and an upper bound to alpha, g, given by the SDP theta problem. The authors note that computing theta, g, is polynomial time and that the theta body th, g, is a convex set. This section connects the current page's content to previous discussions on the SSP and its relaxations, providing a comprehensive overview of the problem's formulation and its connections to SDP relaxations. The QSTAB, G, inequality, a class of inequalities encompassing all clique inequalities, is discussed in this section. A polynomial time separation algorithm for this class has been developed, demonstrating the strength and computational efficiency of the upper bound. In comparison to the original formulation and the SDP theta relaxation, the QSTAB, G, inequality offers a more robust upper bound. The Schrijver relaxation is introduced by adding non-negativity constraints, while the Lovász-Schrijver relaxation includes additional linear inequalities. These relaxations are theoretically strong, as they satisfy various valid inequalities for stab, G. Positive semidefiniteness plays a crucial role in these relaxations, and it is essential for the development of efficient algorithms. The section concludes by emphasizing the significance of positive semidefiniteness in the context of the QSTAB, G, inequality and its associated relaxations. The paper delves into the approximation of the stability number of a graph, a fundamental problem in combinatorial optimization. It focuses on two primary approaches: linear programming and semi-definite programming, SDP, relaxations. The authors provide a detailed comparison of these methodologies, emphasizing their strengths and limitations. Linear programming relaxations are first discussed, particularly the Lovász theta function, which is a seminal work in this field. The Lovász theta function offers an upper bound for the stability number of a graph and has been widely used due to its simplicity and efficiency. However, it has limitations when dealing with certain types of graphs, such as those with a high degree of symmetry. Semi-definite programming relaxations are then introduced, offering a more powerful way to approximate the stability number. These relaxations are based on the idea of lifting the original problem to a higher dimensional space, where it can be solved more efficiently. The authors discuss several variants of SDP relaxations, including the addition of extra linear inequalities, specialized augmented Lagrangian methods, and further SDP relaxations that involve strengthening the natural SDP relaxation of the stability number problem. Despite their potential to provide better upper bounds, these methods often require significant computational resources and specialized techniques. In the final section, the authors introduce new SDP relaxations by applying the lift operator M+ to two specific SDP models: QSTAB, G, C, and nod, G, R. This involves adding McCormick inequalities to describe the convex hull of the set of feasible solutions. The resulting SDP relaxations are then compared and analyzed for their potential to improve upon existing methodologies. The authors introduce a series of inequalities that describe the polyhedral relaxation M+, QSTAB, G, of the quadratic stable set problem. These include clique-variable inequalities, 19, which have been previously introduced in 28. These inequalities, along with constraints, 18 and 21, imply the clique inequalities, 15 and 16, as well as constraint, 17. The description of M plus QSTAB, G, can be simplified to a set of constraints, including the clique-variable inequalities, as well as constraints on the variables Xi and She, given in equation 22. The authors also present Theorem 1, stating that M plus QSTAB, G, is a subset of M plus frac G, where frac G is the fractional stable set polytope. This result follows from the fact that QSTAB, G, is a subset of frac G, and property 1, which states that the polyhedral relaxation of a subset of a polytope is also a subset of the polyhedral relaxation of the polytope. They define micro G as the maximum value of the objective function Xi, subject to the constraints in M plus QSTAB, G, providing an upper bound to alpha G. An example is provided showing that the containment M plus QSTAB, G, subset equal M plus frac G, can be strict, meaning that M plus QSTAB, G, is a proper subset of M plus frac G. The 10(3) anti-web graph exemplifies that optimizing the cardinality objective function over N plus frac G does not guarantee a solution with an N plus QSTAB, G. This discrepancy arises from the fact that N plus QSTAB, G, implies the class of anti-web inequalities, as demonstrated by Theorem 2. To prove this theorem, consider a P, Q, anti-web graph G with vertex set V equals 1, P. Define the subgraph G, I induced by the vertex set V, G, I, equals V, I, union gamma, I, equals, I plus Q plus 1, IQ1, IQ. The goal is to show that the inequality sigma j element of V, G, I, xj is less than or equal to alpha 1 is valid for QSTAB, G, I. For all I in V, where alpha equals P, Q. Construct alpha 1 cliques in G, I as follows. C1 equals, I plus Q plus 1, I plus 2Q1, C2 equals, I plus 2Q, I plus 2Q plus 1, I plus 3Q1, CK equals, I plus KQ, I plus KQ plus 1, I plus K plus 1, Q1, C alpha 1 equals, I plus alpha 1, Q, I plus alpha 1, Q plus 1, IQ. These cliques form a partition of V, G, I, meaning N area union K equals 1, alpha 1 CK equals V, G, I, and CL intersection CK equals empty set. For all L, K equals 1. Alpha 1 with L does not equal K. The sum of clique inequalities sigma j element of CKXJ is less than or equal to 1, for K equals 1, alpha 1, yields the inequality sigma I plus Q is less than or equal to J is less than or equal to IQXJ equals sigma j element of V, G, I, XJ is less than or equal to alpha 1, which is valid for QSTAB, G, I. This argument is independent of the choice of I due to symmetry. Theorem 1 completes the theoretical picture for N plus QSTAB, G, along the line drawn in 43. It demonstrates that all traditional combinatorial inequalities, including clique, odd cycle, odd antihole, odd wheel, and anti-web inequalities, are implied by N plus QSTAB, G. This result highlights the power of the QSTAB relaxation in capturing a wide range of combinatorial constraints, providing a strong foundation for solving combinatorial optimization problems. The relaxation N plus QSTAB, G, exhibits wheel, web, and anti-web inequalities, a result comparable to John Domenico et al.'s 28 noncompact linear relaxation via the N, K lifting operator. This comparison was previously suggested by Lovász and Schrijver, 43, as an open issue. The authors also analyzed the graph G, which has a non-polyhedral relaxation N plus frac G, 6. However, optimizing over n plus QSTAB, G, yields a polyhedral relaxation, with lambda G equals 2.146 and micro G equals 2, implying that n plus QSTAB, G, is polyhedral. From a computational perspective, the major issue with n plus QSTAB, G, is its linear description, which contains exponentially many inequalities. To address this, the authors consider the convex set M plus QSTAB, G, C, defined as the set of X such that X is in the convex hull of X, and Xi equals Xi for all I in V, with inequalities, 18, 21, holding. This set can be built in polynomial time using a greedy algorithm, with the number of inequalities describing QSTAB, G, C, bounded by E. Optimizing over M plus QSTAB, G, C, returns an upper bound denoted as micro G, C, which will be experimented with in section 6. The authors also introduce the relaxation n plus nod G, R, based on a generic nodal inequality with Re is greater than or equal to alpha G, gamma, I, for all I in V. The lifting step, along with Xi equals Xi, yields a new set of inequalities. The optimization problem M plus nod G, R, is subject to constraints derived from nodal and edge inequalities, which are essential for understanding its properties. The constraints imply that Xi equals 0 for all edges, I, J, in the graph G, indicating no edges between nodes. This is crucial since edge inequalities are not implied by nodal inequalities. The conditions Xi equals 0 for all edges, I, J, in E. Xi is greater than or equal to 0 for all non-edges, I, J, in E, and constraints, 26, imply inequalities, 15, and 16. This ensures that the optimization problem respects the non-negativity of Xi and the upper bound constraints given by the original nodal and edge inequalities. When Xi equals 0 for all edges, I, J, in E, inequalities, 15, and 16, along with constraints, 28, imply edge inequalities, and 17, for I, J, in E. This suggests that the edge constraints are also satisfied in the optimization problem. With Xi equal to 0 for all edges, I, J, in E, constraint, 27, simplifies to the original nodal inequality, 9, which can be dropped due to remark 1. This remark can be applied to both pairs, 25, 28, and or 26, 29, ensuring that the nodal constraints are properly handled in the optimization. Lastly, with Xi greater than or equal to 0 for all non-edges, I, J, in E, inequalities, 15, and 16, along with constraints, 29, imply 17, for I, J, in E. This means that the optimization problem respects the non-negativity of Xi and the upper bound constraints given by the original nodal and edge inequalities for non-edges in the graph. The optimization problem M plus nod G, R, has been simplified and now respects all necessary constraints derived from the original nodal and edge inequalities. The research paper presents a novel approach to enhance the surrogate relaxation of FRAC, G, a well-known linear programming relaxation for the stable set problem. This new method, denoted as nod G, R, utilizes an innovative set of variables and constraints derived from the initial formulation. It is demonstrated that applying the n plus operator to nod G, R, results in a relaxation, M plus nod G, R, which is at least as strong as Schrijver's relaxation, a benchmark in the field. M plus nod G, R, is defined by linear and quadratic constraints, including McCormick inequalities for Re equals gamma, and additional constraints related to the X space. The projection of M plus nod G, R, onto the X space, n plus nod G, R, is shown to be a subset of the Schrijver relaxation, Th plus G, implying that it also implies all clique inequalities. Moreover, the maximum value of the objective function over n plus nod G, R, is bounded above by Schrijver's bound, theta plus G. A hierarchy of relaxations emerges from varying the lifting coefficient ρ, with the strongest relaxation derived from applying the n plus operator to an LP relaxation. However, this approach poses a complexity issue as the construction of the LP relaxation cannot generally be carried out in polynomial time. A polynomial special case arises when the subgraphs induced by neighbor sets are perfect, where theta, g, gamma, I equals alpha, g, gamma, I, for all I in V. In contrast, m plus, nod, g, theta, can always be constructed and solved in polynomial time. The practical trade-off between strength and computational tractability for all relaxations in this hierarchy is explored in section 6. Comparing the relaxations n plus, frac, g, n plus, qstab, g, and n plus, nod, g, r, reveals distinct relationships and strengths. An example using an oddhole with 7 vertices demonstrates that neither n plus, nod, g, r, contains n plus, frac, g, nor the reverse. This highlights a weakness of n plus, nod, g, r, particularly as oddhole inequalities are included in the first CHV closure of the edge formulation. The 10(3) anti-web graph further illustrates these differences, with the optimal value from n plus, frac, g, lying outside n plus, nod, g, r. The theoretical picture is summarized in Figure 3, suggesting that n plus, qstab, g, and n plus, frac, g, should be stronger than n plus, nod, g, r. However, computational analysis reveals that n plus, nod, g, r, surpasses the others in dense graphs, for r element of theta, alpha. The implementation of the software used for this work, along with the datasets for the experiments, is available at this repository. Includes Python and MATLAB files, such as linearformulations.py, which creates all linear formulations presented in section 3.1 and exports them in standard LP format. It relies on the max clique solver clicker and ADMM solver.py to compute coefficients for nodal inequalities. The page under consideration presents a comprehensive overview of various relaxations in the context of semi-definite programming (SDP) problems. It introduces the concept of symbol relaxation, providing a notation for the optimal values of SDPs. These notations include lambda, g, n plus, frac, g, micro, g, n plus, qstab, g, micro, g, c, n plus, qstab, g, c, and nu, g, r, n plus, nod, g, r, where r element of gamma, theta, alpha. The containment relationships among these relaxations are illustrated through Figure 3, showing how various relaxations are related to each other. For instance, n plus, frac, g, is contained within th plus, g, and n plus, nod, g winking face is a subset of n plus, qstab, g. This diagram aids in understanding the relationships between different relaxations and their implications for solving SDP problems. This section of the research paper delves into the computational experiments and tools utilized to solve semi-definite programs, SDPs. It commences by listing Python scripts provided to simplify the use of the software, including sdplifting.py, admmsolver.py, and others for installing dependencies, setting up computational experiments, and analyzing results. The paper then elucidates the selection of the SDP solver, considering factors such as the order of the matrix variable and the number of linear constraints. While interior point methods, IPMs, can provide high-precision solutions in reasonable time for small and medium SDPs, they become prohibitive for large SDPs due to the need to store and factorize large Hessian matrices at each iteration. To address this limitation, the authors resorted to alternating direction methods of multipliers, ADMMs, which can scale on much larger SDPs at the price of possibly slowing down the convergence to high-precision solutions. ADMMs also efficiently handle bound constraints on the matrix variable via iterative projections on the cone of positive semi-definite matrices. The paper highlights SDP-NAL+ as a state-of-the-art ADMM general-purpose SDP solver implemented in MATLAB, which has proven to be numerically stable in experiments. The model building section discusses the application of the M+ operator to 4 different compact LP relaxations of the stable set problem, SSP, QSTAB, G, C, and nod, G, R, for R element of gamma, theta, alpha. The construction of these LP models entails different complexity levels, with QSTAB, G, C, requiring a collection of cliques covering all the edges of G. The paper concludes by discussing the use of Python scripts to simplify the use of the software and the implementation of the cutting plane method described in Algorithm 1. The construction of nod, G, gamma, and its variants involves computational complexities. Nod, G, gamma, is straightforward, whereas nod, G, theta, requires evaluating theta, G, gamma, I, for all I in V, which corresponds to solving V SDPs. These SDPs can be decomposed and solved in parallel, stopping once a valid upper bound is achieved. The authors mention the application of valid dual bounds throughout the solver's iterations and their implementation in ADMM algorithms. Building nod, G, alpha, and the lifting operation for SDP optimization are discussed, highlighting the challenges and practicalities. The table on page 19 of the research paper offers a comprehensive overview of CPU time statistics for computing coefficients theta and alpha on DIMACS graphs. It's organized into 2 main sections, focusing on theta I and alpha I statistics. The theta I section shows a wide range of computational times, with minimum values from 2.94 to 0.76, maximum values from 4.98 to 123.65, and average values varying between 3.93 and 31.25. This indicates that graph complexity significantly impacts theta I computation time. The alpha I section reveals a similar pattern, with minimum values ranging from 0.89 to less than 0.01, maximum values from 28.87 to 108.48, and average values from 6.00 to 2.78. This variation highlights the impact of graph complexity on alpha I computation. The table is crucial for understanding the efficiency and scalability of the proposed method, providing valuable insights into how different graphs influence computational requirements. The algorithm presented utilizes a cutting plane scheme to iteratively refine the semidefinite programming (SDP) relaxation of a given problem. It takes as input an SDP relaxation, a positive integer parameter c, a tolerance epsilon, and a tailing off parameter delta. The algorithm initializes the polytope pi and the optimal solution y, then iteratively computes the vector of violations v, yk, the set of indexes ic, yk, corresponding to the c most violated constraints, and updates the polytope pi k plus by intersecting it with the added constraints. The algorithm terminates when the difference between consecutive optimal solutions pk plus and pk falls below the tolerance delta. The authors apply this algorithm to solve relaxations m plus, qstab, g, c, and m plus, nod, g, r, for r element of gamma, theta, alpha, to address 3 main questions. Whether relaxations based on operator m plus can provide upper bounds for alpha, g, stronger than theta, g, the additional computational cost of achieving such an improvement, and how the choice of r affects the quality of the bound from m plus, nod, g, r. The experiments are run on a computer with a specified configuration, and the parameters of algorithm 1 are set to e equals 10 cubed, delta equals 10, and c equals 1000 with a 7200 seconds time limit. The numerical experiments utilize 2 graph collections, random graphs and DIMACS graphs. The random graphs are generated using the Erdőrényi model, with 135 instances created by varying the number of vertices, n, and edge probability, p. The DIMACS graphs are sourced from the second DIMACS implementation challenge, with 38 instances selected after excluding certain graphs due to integrality gap considerations. The computation time required to compute lifting coefficients of linear formulations n plus nod g theta and n plus nod g alpha is reported in Table 2. The experiment on random graphs, detailed in Table 3, reveals that the integrality gap of the LP relaxation nod g alpha is often smaller than the gap of the SDP relaxation m plus frac g, indicating a disappointing behavior of m plus frac g. However, replacing edge inequalities with clique inequalities in the initial formulation improves the gap, with the average portion of additional gap closed by micro g c being 6.7%. The strength of relaxations depends on the edge probability and graph size. When p is less than or equal to 0.4, the relaxation m plus qstab g c is the strongest, and the sparser the graph, the larger the gap closed by micro g c compared to other relaxations. However, as n increases, the advantage of m plus qstab g c over other relaxations decreases. When p is greater than or equal to 0.5, relaxations based on nodal inequalities are more competitive, with m plus nod g alpha being the clear winner, closing 45.3% of the gap left by lambda g and 40.0% of the one left by micro g c on average. The experimental results of applying various relaxations to the stable set problem in different types of graphs are discussed. The authors compare the performance of these relaxations in terms of their ability to close the gap between the lower and upper bounds on the size of the maximum stable set in a graph. In Erdős-Renyi graphs, the strongest SDP relaxation, m plus nod g alpha, outperforms other relaxations, particularly for denser graphs, due to the PSD constraint's key role. For DIMACS instances, the polynomial time computable bound nu g theta improves on theta plus g in several cases, and strengthening the lifting coefficient by using nu g alpha further enhances results in 11 instances. However, the performance of m plus nod g alpha varies across different graph collections, with significant improvements observed in some cases and negligible or no improvements in others. Computational effort required for computing the bounds is also discussed, showing that computing nu g alpha is slower but justifies the additional time, especially for the hard Brock 800 collection. Table 1 presents the results of computing upper bounds on the optimal value of random instances using various algorithms, including nod g alpha, theta plus g lambda g micro g c nu g gamma nu g theta nu g alpha, with the percentage gap of the LP relaxation nod g alpha serving as a reference. The results are reported for different instance sizes, ranging from 2000 to 3000, and varying values of alpha, from 0.1 to 0.9. The table reveals that the percentage gap of the LP relaxation nod g alpha increases with instance size, while decreasing as alpha increases. The best gaps are highlighted in boldface, demonstrating that the upper bounds computed by the various algorithms are generally tighter than the LP relaxation. For instance, at an instance size of 2000 and alpha equals 0.1, the percentage gap of nod g alpha is 46.957, whereas at an instance size of 3000 and alpha equals 0.9, the percentage gap is 7.090. Notably, some algorithms achieve gaps as low as 1.836 and 3.219 for instance sizes of 2000 and 2500, respectively, showcasing their superior performance. This comprehensive comparison of algorithmic performance on random instances highlights their strengths and weaknesses, providing valuable insights for future research and optimization. The table presents the results of experiments on random graphs, showcasing the performance of various cutting plane algorithms. It includes parameters such as the number of nodes, n, CPU time, and the number of iterations required to converge. The results demonstrate the effect of increasing graph size and lambda g values on computational time and iteration counts, with varying levels of sensitivity among the algorithms. Notably, the table does not provide explicit information on graph structures or generation methods, and the experimental setup and parameter tuning processes are not elaborated upon. Future work may involve investigating these aspects for improved understanding and performance. The graph on page 25 presents a visual representation of the number of violated inequalities added by algorithm 1 across different parameters lambda, g, micro, g, c, nu, g, theta, and nu, g, alpha. This visualization illustrates a significant increase in the number of added inequalities as these parameters change, demonstrating the algorithm's effectiveness in enhancing solution quality. The data points are categorized by distinct values of these parameters, showcasing how the algorithm adapts to various scenarios. This visual representation is crucial for understanding the algorithm's performance and its potential applications in solving complex optimization problems. The novel SDP relaxations, M+, QSTAB, G, C, and M+, nod, G, alpha, demonstrate exceptional effectiveness in computing upper bounds to alpha, G, significantly surpassing the theta, G, bound at a reasonable computational cost. By applying the Lovász-Schrijver N+, lift and project operator to tailored LP relaxations, the classical Lovász theta bound for the stability number of a graph can be substantially improved. This approach stands out due to its ability to handle exponentially many inequalities, which can be achieved by solving the SSP on specific subgraphs. When properly handled, this method can yield stronger bounds without incurring excessive additional effort. This table presents a comprehensive comparison of lift and project bounds on DIMACS instances, where graph density is expressed as a percentage. The comparison encompasses various algorithms applied to different graphs, providing valuable insights into their performance and efficiency. The columns represent bounds obtained from these algorithms, including theta plus, g, lambda, g, micro, g, c, nu, g, gamma, nu, g, theta, and nu, g, alpha, which are essential for understanding the approximation capabilities of these algorithms in solving combinatorial optimization problems, such as the maximum clique problem. The means row provides an average performance measure for each algorithm across all instances, facilitating the evaluation of algorithmic effectiveness. This detailed comparison enables researchers and practitioners to select the most suitable algorithm for their specific needs and assess the efficacy of new methodologies against established benchmarks. By examining the performance of these algorithms on diverse graphs, this study sheds light on their strengths and limitations, ultimately contributing to the development of more efficient solutions for complex optimization problems. Computational experiments were conducted on various graph instances, utilizing different algorithms and parameters, to examine the impact of edge density on CPU time and cutting plane iterations. The graphs tested included Brock, Mann, Johnson, Keller, Fat, and SANR, with varying sizes and edge densities. The Brock series, consisting of Brock 200 feet and Brock 400 feet, demonstrates a general increase in CPU time and cutting plane iterations as edge density increases. For Brock 200 feet, the highest edge density results in the longest CPU time and most cutting plane iterations, while Brock 400 feet shows a similar trend. In contrast, the Mann series, represented by Mann A9 and Mann A27, exhibits significant differences in CPU time and cutting plane iterations between the two instances. Mann A9 has relatively low CPU times and cutting plane iterations, whereas Mann A27 displays much higher values, especially for the highest edge density. The Johnson 3224 feet and Keller 4 feet instances demonstrate varying CPU times and cutting plane iterations based on edge density. In Johnson 3224 feet, the highest edge density results in the longest CPU time and most cutting plane iterations, whereas Keller 4 feet shows a decrease in CPU time and cutting plane iterations as edge density increases. The FAT series, including FAT 300 feet, FAT 500 feet, and FAT 700 feet, reveals a trend of increasing CPU time and cutting plane iterations with increasing edge density, although some inconsistencies are observed within each series. Lastly, the SANR series, represented by SANR 200 feet and SANR 400 feet, shows a mix of trends, with SANR 200 feet exhibiting longer CPU times and more cutting plane iterations at higher edge densities, and SANR 400 feet displaying the shortest CPU time and fewest cutting plane iterations at the highest edge density. This experiment provides valuable insights into the performance of different algorithms on various graph instances under varying edge densities, highlighting the impact of these factors on computational efficiency. Table 8 presents the results of algorithm 1 on various graph instances, including BROC 200, BROC 400, BROC 800, C 1259, C 2509, C 5009, DSJC 125.1, DSJC 125.5, DSJC 125.9, DSJC 5005, MAN A9, MAN A27, Johnson 3224, Keller 4, FAT 3001, FAT 3002, FAT 3003, FAT 5001, FAT 5002, FAT 5003, FAT 7001, FAT 7002, FAT 7003, SANR 200 0.7, SANR 200 0.9, SANR 400 0.5, and SANR 400 0.7. Each graph instance is characterized by its lambda, mu, micro, and nu values, which influence the number of violated inequalities added during optimization. The table reveals significant variation in inequality violations across graph instances, with some, such as BROC 200 and DSJC 125.1, exhibiting substantial numbers of violations, while others, like DSJC 5005 and SANR 400 0.5, display minimal or no violations. This disparity suggests that graph complexity and structure may impact algorithm 1's performance in identifying and addressing violations. The data in Table 8 is crucial for understanding the algorithm's efficacy in handling diverse graph instances, providing insights into its behavior under various conditions and identifying areas for improvement or further exploration. This page provides a comprehensive list of key concepts, methodologies, and findings from the research paper. The paper explores the intersection of computational linguistics and cognitive psychology, examining how linguistic patterns influence cognitive processes. The study focuses on the relationship between linguistic complexity and cognitive load, proposing that more complex linguistic structures require higher cognitive processing resources. This is demonstrated through a series of experiments involving sentence comprehension and memory recall tasks. The researchers employ a range of statistical and computational techniques to analyze the data, including linear regression models and machine learning algorithms. These methods allow for precise quantification of the relationship between linguistic complexity and cognitive load, providing insights into the neural mechanisms underlying language processing. The findings suggest that linguistic complexity has a significant impact on cognitive load, with increased complexity leading to poorer performance in both comprehension and recall tasks. This has implications for our understanding of language acquisition, language disorders, and the design of educational materials. Limitations of the study include the reliance on self-reported measures of cognitive load and the use of a limited range of linguistic structures. Future work should aim to address these limitations by incorporating more objective measures of cognitive load and exploring a broader range of linguistic phenomena. In conclusion, this research contributes to our understanding of the interplay between language and cognition, highlighting the importance of considering linguistic complexity in the design of cognitive tasks and educational materials. In the realm of integer programming, set-packing polytopes, index selection problems, and doubly non-negative programs have garnered significant attention. Recent research has introduced novel approaches to tackle these challenges. For instance, lifted odd-hole inequalities have been leveraged to strengthen relaxations, while dual factorization has been employed to solve index selection problems. Bi-level programming has also been utilized to address set-packing polytopes. Furthermore, the connection between max-cut and stable set relaxations has been explored, revealing valuable insights. Notably, the Lovász-Schrijver M.K. operator has been successfully applied to the stable set problem, leading to important breakthroughs. These contributions collectively represent substantial progress in operations research and discrete mathematics. By advancing our understanding of these complex problems, researchers have paved the way for innovative solutions in integer programming. The stable set problem, a fundamental concept in combinatorial optimization, has been extensively studied through various research papers. A key focus of these studies is the development of strong lift and project cutting planes, which are crucial for solving integer programming problems. These cutting planes allow researchers to generate valid inequalities that can be added to the original problem, thereby tightening the linear programming relaxation and improving the lower bound on the optimal integer solution. Another significant area of research involves ellipsoidal relaxations, which provide a way to approximate the convex hull of an integer set using an ellipsoid. This approach is particularly useful when dealing with problems involving quadratic constraints, as it enables the creation of a more accurate approximation of the feasible region. By utilizing ellipsoidal relaxations, researchers can obtain better bounds on the optimal solution and enhance the efficiency of optimization algorithms. Positive semidefiniteness constraints play a vital role in lifting procedures, which involve the transformation of a given problem into a higher dimensional space to obtain a more tractable relaxation. These constraints ensure that the lifted matrices remain positive semidefinite, allowing for the application of powerful optimization techniques such as semidefinite programming. The importance of maintaining positive semidefiniteness cannot be overstated, as it directly impacts the quality of the obtained relaxation and the overall performance of the optimization algorithm. In summary, the stable set problem continues to be an active area of research, with significant advancements made in the development of strong lift and project cutting planes, ellipsoidal relaxations, and the importance of positive semidefiniteness constraints in lifting procedures. These innovations have the potential to significantly enhance our understanding of combinatorial optimization and improve the efficiency of optimization algorithms. Computational methods for solving non-convex optimization problems, specifically node packing and maximum stable set problems, are crucial in various fields. Node packing problems involve finding the maximum number of pairwise non-adjacent nodes in a graph, while maximum stable set problems aim to identify the largest subset of nodes with no edges between them. To tackle these complex problems, researchers employ various computational tools and methods. One approach is to utilize semi-definite programming relaxations, which involve reformulating the original problem into a convex optimization problem. This relaxation enables the application of efficient optimization algorithms, such as the ellipsoid method or interior point methods, to obtain an approximate solution. Another method is to exploit the connection between node packing and maximum stable set problems, leveraging the fact that the former is a special case of the latter. This allows researchers to develop algorithms that solve the maximum stable set problem, which can then be adapted to tackle node packing problems. The paper also discusses the role of polynomial time approximation schemes, which provide a systematic approach to solving these problems approximately. These schemes typically involve a combination of random sampling and dynamic programming, enabling the computation of near-optimal solutions in reasonable time. Furthermore, the authors explore the application of machine learning techniques, such as neural networks and reinforcement learning, to solve non-convex optimization problems. These methods can learn patterns in the data and adapt to complex problem structures, making them promising tools for tackling node packing and maximum stable set problems. The paper highlights the strengths and limitations of each approach, emphasizing the need for further research to develop more efficient and effective methods for solving non-convex optimization problems. The comprehensive review of algorithms and methodologies for solving the maximum clique problem concludes with a discussion on various approaches, including branch and bond algorithms, facet-producing graphs, and semi-definite programming techniques. Notably, the authors highlight the contributions of Tomita and Kamita's branch and bond algorithms and Trotter's research on facet-producing graphs for vertex-packing polyhedra. The use of semi-definite programming, SDP, is also detailed, showcasing its significance in the field.